Good morning. My name is Sarah Stewart. I'm the president of the Planetary Science section. Welcome to the 2017 Sagan Lecture. The Sagan Lecture honors the life and work of Carl Sagan. Trained in astronomy and biology, Sagan was a leader in establishing the field of astrobiology. He was also a tireless educator, author, and space advocate. The Sagan Lecture is co-sponsored by the Biogeosciences section and the Planetary Science section. Sagan was a co-founder of the Planetary Society, and the mission of the Society is an apt description of the Sagan Lecture: to know the cosmos and our place within it. The 2017 Sagan Lecturer is Jonathan Lunine. Jonathan is a professor at Cornell University and the director of the Cornell Center for Astrophysics and Planetary Science. Jonathan embodies the spirit of the Sagan Lecture. His body of research has advanced our understanding of brown dwarfs, planet formation, evolution, and habitability. He is a dedicated educator and author of 2 textbooks on planetary habitability. And he is a vocal advocate of exploration in the search of understanding the origins of life, and he's also a valued advisor in planet exploration mission planning. Please welcome Jonathan Lunine, who will argue that exploration of the solar system's ocean worlds is a scientific and societal imperative. Congratulations, Jonathan.
Great, thank you, Sarah. Good morning. It's a pleasure and an honor to be asked to give the Carl Sagan Lecture. And I want to thank both sections, the Planetary Science section and Biogeochemistry sections, for this opportunity. Carl Sagan was one of my scientific heroes, probably the scientific hero when I was a teenager. And like a number of other planetary scientists that I know, Carl wrote to me as when I was a teenager, and I was inspired by his books, and so I wrote a letter to him, actually encouraged by my mother because I didn't believe he would write back. And sure enough, he wrote back, and he did that for many other people, and I'm looking at some faces in the audience where I know the same was true. That kind of dedication to communicating with students is something that we all hopefully aspire to. I'm not sure we all do it with the same capacity for energy and passion that Carl did, but it was very important in my career. I want to, in this talk, as Sarah alluded to, argue that we're at the point now where there are several bodies in the outer solar system where we must begin to focus our exploration, not necessarily to the exclusion of others, but certainly because these are special places. And these are a subset of what are now called the ocean worlds of the outer solar system. I'll give a little bit of a history along with the scientific imperative, and the purpose of the history is to argue that a key goal for this kind of exploration, which is looking for evidence of life, is something that in planetary science we have something of a love-hate relationship with. And I want to explore at the beginning of the lecture what I think may be a little bit of the origin of that love-hate relationship and try to dispel it for future exploration. And then I will go ahead and talk about the societal implications at the end. And now, oh, there it is. Okay. The button. Okay, good. So let me start with the scientific imperative. And I'm going to begin in 1966, which was just 4 years after the first successful interplanetary exploration mission, Mariner 2, to Venus. That mission, of course, showed or gave a strong hint that Venus was uninhabitable. It wasn't definitive. But this was also a time where a lot of discussion was going on about both the question of how life began on the Earth and how life might be detected elsewhere in the solar system. And Carl Sagan at that time in 1966 co-authored an English translation of a book originally authored alone by Josef Shklovsky in the Soviet Union called Intelligent Life in the Universe, which is one of Carl's least known books, but was actually a tour de force of the scientific synthesis going from the origin of the cosmos to the origin of life and its occurrence on other worlds, and one which was written 50 years ago. In that book, and it's an interesting book because the two authors didn't try to merge their text. Shklovsky's text was translated into English, and Carl Sagan put his own text in carets, separated from Shklovsky's text. So you could tell who wrote what. And Sagan said that the discovery of life on one other planet, for example, Mars, can, and now he quotes a physicist, Philip Morrison, who was then at MIT, had just moved from Cornell, can, in the words of the American physicist Philip Morrison, transform the origin of life from a miracle to a statistic. And while our laboratory studies and computer models of the origin of life on Earth today are much more sophisticated than they were 50 years ago, we're still in that same situation as we were a half century ago. And I would argue that we likely will not be out of that situation even if we have very deep insights from laboratory and computational work. Because to find another form of life elsewhere outside of Earth and to demonstrate that it had an independent origin is the beginning of developing the same kind of statistics of the occurrence of this phenomenon that we have for other physical phenomena in the cosmos. We don't have that yet. Now, Sagan said this at a time, actually just after, 2 years after Mariner 4 had flown by Mars, taken images of a heavily cratered surface, and changed people's perspective about Mars as a possible abode for life in a very negative way. Now, if we fast forward to 1971, on the eve of the Mariner 9 orbit insertion around Mars, Caltech and JPL had organized a remarkable encounter among scientists, journalists, and science fiction authors. Sagan and Murray, Walter Sullivan from the New York Times, and two of the best-known science fiction authors, Ray Bradbury and Arthur C. Clarke. And in that encounter, Arthur C. Clarke made the remarkable claim, mostly based on what was seen of Mars from Mariners 4, 6, and 7, not because he had any insight into the Jupiter system. His view of the Jupiter system is shown on the right-hand side, which is the fantasy of the alignment of the Galilean moons before the monolith shows up. But what he said was, I think the biological frontier may very well move past Mars out to Jupiter, which I think is where the action is. And that was a very prescient thing to say. Even though Mars has turned out to be incredibly fascinating, we also know that the outer solar system is incredibly fascinating and may indeed be a place, certainly is a place with habitable environments and a place where life might actually be present. Now, Sagan himself agreed with this, essentially. In his 1973 book, The Cosmic Connection and Extraterrestrial Perspective, which was actually the book that motivated me to write to him, on page 195, he says a number of things that are quite important. The most significant is at the bottom of the red box, and that is that organic compounds are suspected to be present in the outer solar system, including in the Jupiter system and on Titan. Now, we knew that Titan had methane. That was discovered by Gerard Kuiper, his advisor at Chicago, back during World War II. But we didn't know whether, or they didn't know whether other organic compounds were present. And the other thing that Sagan said that was important was that not only were astronomers needed in planetary science, but also geologists, chemists, physicists, and biologists. And the field at that time was kind of split between the geological and geochemical side and the astronomical side. And part of this book was trying to put that together, which was, I think, very important. Now, in the midst of all this discussion, NASA had very aggressive plans for the exploration of Mars, and they culminated in the Viking landings in 1976. Those two landers carried with them biological experiments to test for evidence of life. They also carried mass spectrometers. And as we all know, the results were ambiguous, but the results that suggested the possibility of life were later understood to be the result of the very high chemical reactivity of the soil, which had nothing to do with biology. And it's generally felt within the community that the Viking biological experiments were something of a mistake that set planetary science, or at least Mars exploration, back a number of years. I agree partially with the first of these because, in fact, we now know that before you do the biological experiments, you must understand the physics and chemistry of the planetary environment. And we didn't understand that for Mars, or they didn't understand that at the time. On the other hand, the kinds of instruments that one would want to put in orbit that could tell you the things you needed to know to either do or not do these experiments were really not available at the time. And so even if this had been done in a more progressive way, we might still be at the same stage of Mars exploration. There would effectively not have been any delay. There would have simply been a delay in the Viking experiments. And in fact, they might never have been done. And I think they were a useful lesson to us as to how to do the search for life in the solar system. Now, it is true that subsequent to the Viking missions, planetary exploration entered a very dark period, but much of this was due to things unrelated to Viking. The NASA upper administration, exemplified here by Hans Mark, the deputy administrator, had turned away from planetary exploration, not because of the Viking results, but because they wanted to emphasize the shuttle and the development of a space station, which Hans Mark said would then be used to send humans out into the solar system to do the exploration. And that was his model for doing solar system exploration. He was not so interested in robotics. And if anyone wants to draw an analog to the present political situation, you're free to do that. I think it's very different, but this does come up, of course, periodically. The other things that happened were the U.S. missed the opportunity to send a spacecraft to Comet Halley with the Europeans and the Russians because we had an unfavorable political climate in Congress as well as at NASA. Challenger disintegrated in 1986, the same year as the Halley expeditions, and that meant that there was no way to launch the Galileo spacecraft to Jupiter. And indeed, it wasn't clear after that accident, which was, of course, a terrible tragedy that killed 7 astronauts, whether it would be possible to even launch Galileo to Jupiter in any reasonable time. A few years after that, in 1992, the U.S.'s second opportunity to go to a comet was canceled by Congress, the Comet Rendezvous Asteroid Flyby mission. And the pièce de résistance to this terrible decade or so was in 1993, Mars Observer was lost just a few weeks before it was to enter Mars orbit because of a failure in the propulsion system. And so one could be excused for imagining that the Viking missions had somehow created bad luck for the planetary program. But this really was a confluence of many different things that led, essentially a series of unfortunate events that led to a period when, early in my career, it looked like planetary science might not be the right thing to do for a career. But on the other hand, in that same period of time, there were remarkable successes, and those successes, in fact, opened the door to the exploration of the ocean worlds that I'm going to talk about in the second half of my talk. The Voyager missions launched in 1977, flew by Jupiter in 1979, found that the Galilean moons were all very different from each other. Io was volcanically active, Europa was smooth and fractured across its surface, very few craters. And Ganymede and Callisto, even though they were the same size and bulk density, looked to have completely different geologic histories. So suddenly, the moons of the outer solar system became places that had their own individual histories, energy sources that hadn't previously been thought of, like tidal heating, which Peel, Casson, and Reynolds identified and published just weeks before the Voyager 1 flyby of Jupiter as a potential way to generate activity and liquid water inside of these objects. 1980, Voyager 1 flew by Titan, discovered that it did not have a thin veneer of methane, which was a possibility, but had a thick atmosphere instead of nitrogen, with methane as a secondary gas playing something like the role that water plays in the Earth's atmosphere. This opened the possibility for complex organic chemistry because now nitrogen was present as well as carbon and hydrogen. 1981, Voyager 2 imaged Enceladus at relatively high resolution and found that a large part of its surface was smooth, didn't have craters, was very bright, and looked for all the world to be a place that might be supplying the E-ring of Saturn within which it orbits and which was discovered about 15 years before that. And then 1986, Uranus, 1989, Neptune and Triton turned out to be extremely active, had nitrogen geysers, had a surface where the craters had been modified by tidal heating after capture around Neptune, presumably. And so even in the coldest part of the outer solar system, these bodies had a geologic history to them. And then Galileo was successfully launched from the shuttle only 3 years after the Challenger accident, and Cassini managed to survive threats of cancellation and was launched in 1997. So things picked up for the outer solar system during this period that otherwise seemed very difficult. Mars exploration picked up too. I'm not going to talk about that for lack of time, but of course the extraordinary results from a flotilla of orbiters, of landers and rovers is a story unto itself. Now, the results of these missions were such that by 2003, when the National Academy of Sciences published its first decadal survey of solar system exploration, there had been several of these for astronomy and astrophysics, the field was confident enough that you could read in the executive summary that solar system exploration is not only that grand human endeavor whose purpose is to discover the nature and the origin of the system of planets in which we live, but is also an endeavor in which to learn whether life exists beyond the Earth. And so there are these two purposes to planetary exploration in the executive summary of that decadal survey, one of which is to search for life, and in the red area a few lines below, to find out whether we're alone, to answer that question. That doesn't appear quite so strongly in the executive summary of the next decadal survey, although the word life appears in the executive summary almost as many times, in the first paragraph at least, as other nouns do. And so this is embedded within our sense as a planetary community of surveys, even though it's fair to say there is a somewhat dichotomous view about whether we should be utilizing our planetary missions to explicitly go look for life or simply to look at the properties of objects where life might be present. And I'm going to argue that the former is something that we really need to do, and the time is right to do it in the outer solar system. So let me talk about these places. There are a dozen worlds which either have oceans or had oceans in the past, and this may not be a complete list, and it is subject to change. The worlds that are listed as ocean relics, which are Mars, Ceres, and Venus, are places where oceans almost certainly existed in the past. In the case of Ceres, there might be liquid water in the core as a kind of a muddy ocean or a mud ocean. But in the case of Mars, there's ample evidence for standing liquid water in the ancient past in the first billion years. And on Venus, the evidence for the ocean is, of course, the D to H ratio in water in Venus's atmosphere, which is so large that it can't be explained by contamination with comets or other things. Venus lost an ocean or so of water. In the case of the Jovian, Saturnian moons and objects at the edge of the solar system, these are bodies where liquid water is present in their interiors, either based on multiple lines of evidence or, in some cases, one line of evidence. So the degree to which there is a certainty in the presence of these oceans is very different for these objects. I'm not going to go through each one of them. But I want to point out that for the Jupiter moons, and I'm sorry, icy moons is really a misnomer because Europa has a density of 3 grams per cubic centimeter. It's mostly rock, of course. But in the case of the Jupiter moons, the evidence comes from electromagnetism, from measuring magnetic fields inside these bodies. Jupiter has a very non-dipolar magnetic field, And so as it sweeps through these bodies at the rotation rate of Jupiter, the bodies feel a time variable magnetic field. And in the case of Europa and Callisto, there are induced magnetic fields that Galileo measured that can best be explained, indeed perhaps uniquely explained for Europa, as the result of a layer of high electrical conductivity, which essentially requires liquid water doped with something else, ammonia or salt, and almost certainly salt. In the case of Ganymede, the evidence is more complex, having to do with auroras and how they nod back and forth, because Ganymede has its own intrinsic magnetic field. In the case of the Saturnian moons, the evidence is not from the magnetometers, because Saturn's magnetic field is very quiet, dipolar, low in intensity, and so induced magnetic fields are very, very difficult to measure, although not impossible. The evidence comes from a variety of data, including measurements of the mass distribution inside these bodies for Titan and for Enceladus. Evidence in the case of Enceladus for a large libration that requires a decoupled crust from the interior. And there are several moons that are exemplified here in the case by Dione, of places where it looks like there might have been some activity, some plume activity, in that case measured by the magnetometer, or an excess libration in the case of Mimas, which are weak indicators that there might be an ocean. In the case of Titan, it's gravity measurements, tidal distortion as Titan moves in its eccentric orbit around Saturn. And Titan, of course, has these large seas that are not liquid water but are liquid methane that were discovered by remote sensing, the imaging system, the near-infrared mapping spectrometer, and the radar on the Cassini orbiter. And the radar has actually mapped the depth and composition of these seas through a process of sending a signal down at the nadir position, timing when the bounce from the surface and the bottom come back to the spacecraft, and then by measuring the attenuation of the bottom signal relative to the top, it's been possible for us to infer that these really are reservoirs of liquid methane with some nitrogen and possibly some methane. And then in the outer solar system, the evidence is largely geological. Now, I would argue that of this pantheon of worlds, Europa, Enceladus, and Titan are the ones to focus on because we know definitely that they have liquids. The evidence is almost incontrovertible. And furthermore, these liquids are accessible in one way or another. The Europan crust is thin and fractured. Enceladus has a plume of material coming from the ocean spraying out into space. And on Titan, the methane seas are exposed to the surface. There's also an interior water ocean, but that's likely to be inaccessible. So these places are accessible, and we know quite a bit about them. And so I'm going to argue that we are at the point of either determining their habitability in the case of Europa, or actually going to look for life in the case of Enceladus. And Titan is a more complex story that I will talk about there a little bit later. So Europa is the best place for conventional life because it's large. The ocean is bounded at the bottom by rock because the bulk density of Europa, 3 grams per cubic centimeter, tells you that the amount of ice and liquid is confined to about 200 kilometers of this 1,600 kilometer object, radius object, and it's about the size of the Earth's moon. And so the base of the ocean is at a pressure that is lower than the transition to high pressure ices. And so the ice must be at the top and the liquid water is in contact with the rock, which means, given the fact that Europa is tidally heated, the potential for hydrothermal systems to be occurring. Furthermore, this body is large. The ocean is up to twice the volume of the Earth's oceans. That allows for a large amount of chemical gradients, and most importantly, it allows for water-rock reactions to occur over billions of years, over a long period of time. The other interesting thing about Europa is that the surface is exposed to the magnetosphere of Jupiter. The particle radiation is very intense. Water at the surface of Europa, and the surface is almost entirely water ice, undergoes radiolysis to produce various kinds of peroxides, very oxidized species, and as shown by a number of authors, in particular a paper by Vance, Hand, and Pappalardo in 2012, this material could enter the ocean of Europa and provide an oxidant at about a rate that's 1 or 2 orders of magnitude below that for photosynthesis on the Earth, production of oxygen by photosynthesis. Now, what does that oxidant react with? That oxidant reacts with the products of hydration of silicates at the ocean core boundary, which would include hydrogen and possibly, if organics are present, methane and so forth. The problem is that we don't actually know whether that occurs. We don't know whether there are hydrothermal systems. We don't know whether there are organics. We know very little about this ocean. Even the salinity is poorly understood. And so before we go looking for life, and indeed before we go trying to land on some place that might perhaps have ocean material present, we have to do our homework. And the homework that we have to do is very much like what Cassini was able to do at Enceladus during its mission, something that Galileo could not do because it was not instrumented with the kinds of instruments needed to determine habitability. But the Europa Clipper is so instrumented. And even though habitability is only one of many goals of this mission, the instruments, which are depicted here by their acronyms, provide an excellent palette of techniques for determining the habitability of the ocean and whether there's material expressed at the surface. So to give you just a few examples of this, the red instruments, mass specs and SUDA, are mass spectrometers. They are next generation after the Cassini mass spectrometers with much higher mass resolution and sensitivity. They will be able, and this is just an example from a SUDA presentation, to get very high resolution mass spectra to indicate the presence of sulfate hydrates and organic compounds and other things that may be present on the surface and either evaporate to an altitude where the spacecraft will fly by, 25 kilometers, or if there are indeed plumes on Europa, which the Hubble Space Telescope evidence for is accumulating, and I'm becoming more convinced after being a skeptic, actually flying through the plume and measuring this material coming out through the plume directly. Whether those plumes access the ocean or warm ice is something we don't know. The remote sensing instruments shown on the right include ultraviolet spectrometer, which could also measure properties of the plume, camera system, ice, and the near-infrared mapping spectrometer. That near-infrared mapping spectrometer has the capability of identifying organic molecules, particularly in the 3 to 5 micron region of the spectrum. This is a simulation done by an REU student of mine, a summer student, Kelly Whalen from Siena College, looking at spectra of 2 amino acids and showing that they can easily be distinguished at the resolution of the MISE spectrometer. And then finally, instruments that sample the interior, the crust, the radar system Reason, a thermal mapper to look for crustal thermal anomalies, and then a calibrated magnetometer system that will allow the salinity of the ocean to be determined to a much tighter, much better level than what we have from Galileo. This is from Krishan Khurana and colleagues from a review chapter. This is conductivity versus salt concentration. The horizontal lines show the limits from Galileo of the conductivity, which is about a factor of 50 in uncertainty. And for the sea salt curve that you see as the diagonal curve there, that leads to a possible range of salinity from about the salinity of the Earth's oceans, 4 or 5%, down to something that we would consider distilled water. So clearly this is not a tight enough constraint to understand the nature of the ocean, and Europa Clipper will obtain that for us. I want to move on to Enceladus. Enceladus is the easiest ocean to explore because the ocean is being expressed onto the surface. And for that reason, and because Cassini carried with it mass spectrometers that could analyze the plume, as well as other instruments that did remote sensing, we know the most about this ocean of any of these ocean world objects. It is a saltwater ocean. The salt is at about 0.5 to 2% relative to the water. There is hydrothermal activity. I'll get back to the evidence for that on the next slide. Organic molecules have been detected, both light organics and heavy organics, in both the gas and the solid phases. The pH of the ocean has been constrained by measuring the abundances of the salt ions as well as carbon dioxide in the plume. And everything indicates that this is an environment where microbial life, prokaryotic life, could survive. Now, the question of the hydrothermal system is very interesting because, like Europa, Enceladus is mostly rock, but it's much smaller than Europa. It's 1,000 times smaller in volume than Titan, about 500 times smaller in volume than Europa. It does have a rock core, and the pressures are low enough where the ocean is present that the ocean is certainly in contact with the rock core, and of course on top there's an ice cap. But because Enceladus is so small, we don't know how long reactions between the water and the rock might be sustained. There's a lot of work that's been done on this. Suffice it to say that this is still a question mark. But what isn't a question mark is that there are products of hydrothermal processes that Cassini seems to have sampled. One of these is a very small grains, nanometer in size, of silica, SiO2, which were detected in the Saturn system and traced back to Enceladus by the cosmic dust analyzer. And you see a mass spectrum from the cosmic dust analyzer. The relevant portions are in white, and you see mostly silicon and oxygen, SiO2. A very nice model that was put together by that team, Xu et al., to explain the small size of the grains and the fact that the size distribution is very small, is that these grains are from a colloidal suspension in the ocean. And that colloidal suspension is shot out quickly enough through the fractures at the south pole of Enceladus so that the material doesn't have a chance to accumulate. So where does the SiO2 come from? Well, it comes from interaction between the water and the rock at the bottom of the ocean, and it's possible that this is in fact a result of serpentinization or hydration reactions such as the one shown at the bottom, which comes from the Europa paper by Vance and colleagues. Phaolite and water converting to magnetite, silica, and hydrogen. And so the silica is leached out into the water. As the water comes out of the rock and cools, the silica precipitates out. Now, what about the hydrogen? Well, in the last fly-through of the plume that Cassini made, the last of 7, the gas mass spectrometer, the ion neutral mass spectrometer, was used in a particular mode that allowed it to detect native hydrogen that was not the product of collisions of water molecules inside the instrument itself. And that was published by Hunter Wade and colleagues in 2017. A map of where the hydrogen was seen on the surface is shown on the right. And so we have the two products of this hydration reaction that we can see in the plume, and they're both present. Now, if this type of hydration is occurring, then the core is going to be heavily fractured. There'll be water moving through the fractures. A recent paper by Choblet et al. Noted that that's a recipe for enhanced tidal heating in the core, which could certainly explain the presence of the ocean and the presence of this hydrothermal processing going on, the heat being supplied by tidal heating more than by radiogenic heating. And as well, you can imagine other reactions going on. For example, olivine reacting with water and carbon dioxide to make serpentine and methane. The INMS sees both carbon dioxide and methane. The methane may also be a product of direct reaction of CO2 with hydrogen. But one can sum all this up in what I think was a very nice way by Francis Nimmo, that the important lesson from Enceladus is that even small amounts of chemical information can be extremely useful. And we are now at the point with this body where we can ask the question, is there biology going on inside of Enceladus? Now, for Titan, Titan is a much more complex case. In many ways, the processes at the surface, which are numerous, have a certain balance that is somewhat Earth-like. And at the same time, because the materials involved are so exotic and different from the Earth, it's a little bit hard to predict habitability. And I'm focusing now not on the interior ocean, which may be expressed onto the surface, although we don't have evidence for that, but more on the methane lakes and seas. There are interesting planetological issues associated with Titan. One is that its methane nitrogen atmosphere is actually not very reducing, certainly not reducing compared to the giant planets. And so in some ways it does provide a model for potential abiotic organic reactions that went on the surface of the Earth early in the history of our planet before oxygen became abundant. The other interesting planetological issue is that the whole methane cycle on Titan, which is shown in this figure, is different from that of the Earth's water cycle in that the minimum temperature in Titan's atmosphere at the tropopause is warm enough relative to the saturation vapor pressure curve of methane that methane is flowing into the stratosphere at a rate that is orders of magnitude larger than the rate at which water is flowing into our own stratosphere. Looked at another way, from the surface of the Earth to the tropopause, the water abundance drops by 1,000, by 3 orders of magnitude. On Titan, the methane drops from the surface to the tropopause by only a factor of 3. And so methane is flowing out, being photolyzed, destroyed. In a recent paper by Sam Birch and colleagues, the case was made that there's geologic evidence that much larger amounts of methane were present on the surface in Titan's past, perhaps an ocean. And this leads to the notion that we're looking at a body that in some ways is a model both for the escape of water from Venus early in its history and the escape of water from the Earth at a time in 1 billion years or perhaps 2 billion years when the solar luminosity has increased enough that the tropopause temperature in our own atmosphere will be high enough, even with 0 CO2 in the atmosphere, to allow water to flow freely out, and we would then lose our oceans on a relatively short time scale. So these are interesting geological and evolutionary analogs to the Earth that one would want to study with Titan. But as far as life goes, the methane seas might host weird biochemistry. Is it possible to have life in a methane liquid? And the answer is we don't know. There are things about the non-polarity of methane that militate against biology, and there are things about that non-polarity and low temperature that actually favor things like hydrogen bonding as the structural motif for life, something that is not possible in the Earth's oceans. So here are 2 imaginative examples of analog biomolecules on Titan instead of amino acids, an amino cyanoacid from a recent paper by Liv et al. And then at the bottom, acrylonitrile, which has been found in Titan's atmosphere, first by Cassini and then by Alma, functioning as a molecule that can make a container about the size of a virus, which is not only stable but is flexible. And which possibly could host other kinds of organic chemistry in the seas. But again, here we're really operating mostly out of ignorance because we have no example. So what do we do? Well, I would argue that for all 3 of these bodies, we actually want to go look for life. We know there's liquid present. That's been done. The habitability of the environment has been quantified for Enceladus, not so much for the others. We then want to detect biosignatures. In the case of the liquid water environments, are there amino acids present? Are there fatty acids present? What is the pattern of those abundances? Are those patterns indicative of a biogenic origin or an abiotic origin? If the answer is positive, we want to do the things necessary to confirm that life is present, to actually collect a cell that we can analyze back at the Earth or perhaps on a spacecraft, and ultimately understand the biochemistry of the system. So I'm going to go through each of these 3 objects with a proposed program that's a modification of a program that was developed by Brent Sherwood and colleagues. I was a co-author, and is in press in Acta Astronautica. For each of these worlds, there are 3 stages. Stage A is the next step. We've done Galileo and Cassini. What is the next thing to do? Stage B follows on from stage A and usually involves either looking for biosignatures or actually trying to get the life itself that's producing those biosignatures. And then stage C is what I call the science fiction stage of driving around in submarines and so on inside of these objects. I probably won't live to see that stage. I have a slide about that in a minute. The Europa Program. We are doing Stage A. Stage A is a comprehensive investigation of the icy moon's habitability. That is being done, or will be done, once Europa Clipper is launched, and again is superbly instrumented to tell us whether that ocean seems habitable, whether there are organic molecules, the state of the ocean, and whether there is ocean material expressed frequently enough on the surface that one can get to it before the radiation environment destroys the evidence. Stage B is a lander that would land in a place that would be identified by Clipper and would do investigations to look for biosignatures, do a little bit of digging to get below the upper layer, and look for biosignatures in those ocean deposits. And then again, stage C is submarines and so forth. I'm not going to talk too much about those. For Enceladus, we've done the habitability stage with Cassini. And so stage A is going back to Enceladus, doing the simplest possible thing we can do, which is to fly through the plume and identify not only biosignatures, molecular biosignatures if they're present, but to identify enough of them and in enough detail that we can tell whether the patterns are biological or not. So for example, you could look at the abundance patterns of the amino acids and the fatty acids separately to see whether it looks like it's abiotic or instead is biotic. You look at the chemical affinity in the ocean. How close to equilibrium are the reduced and oxidized species? You look at the isotopic distribution. And that's all I put here because that produces a 3-dimensional cube where if all of these things turn out positive for biology, you're in the bottom green corner of the cube. But you don't have to stop with 3 tests. You can do 4 or 5 or 6, enough so that the ambiguities are removed from the chemical analysis. And this is possible to do with simple chemical analysis techniques that we are well familiar with and have been well tested in space. And then the next step for Enceladus would be, if the results are positive, trying to get cellular material. The plume is tenuous enough that cells are not going to be present. One would probably have to go down to the surface to try to find those cells and be able then to analyze them directly. And then stage 3 is science fiction. The Titan program, I would argue, is going to first require a global reconnaissance. Now you might say we've done the global reconnaissance of Titan. We have, but at a spatial resolution that doesn't really allow us to determine whether Titan has had an extensive era or evolution of fluvial erosion, that's methane fluvial erosion, and whether in fact it had a much larger hydrocarbon sea or ocean early in its history. And that's important because we need to understand how long the present remnant seas have been present on the surface. It's interesting from a planetological point of view, but we need to know that from the biological point of view. Could be done from a very capable orbiter, from a lander that flies around perhaps, but you've got to cover a reasonable amount of the surface at high spatial resolution. And then that would be followed perhaps by going to the seas or doing more aerial exploration. That's Titan Mare Explorer, which was proposed a few discovery opportunities ago. One might go to the seas or their shores to look for the chemical evidence that chemical evolution has proceeded beyond the simple organic chemistry in the atmosphere and is doing something different, whatever that different is, and we really don't know. This is going to take a long time. It's going to take a long time because it takes 5 years to get to Jupiter and 10 years to get to Saturn. And so I'm not going to dwell on this plot, and I was not born in 1960. I was born in 1959. But the point is that even to get to the end of stage A for Europa, from the time that that the results from the Galileo orbiter were obtained is a multi-decade process, and it will end sometime in the late 2020s. And then for these other missions, these other bodies, it gets pushed even farther out. And this is the reason why I argue that if we want this to be meaningful from a scientific point of view, there has to be enough continuity, which means that missions have to be started now to at least 2, or ideally 3 of these bodies. And the preparation for stage B of the Europa exploration also has to be done now. That's a fairly aggressive program, but without that, the time duration between these stages will be too long even for the younger people in our field. So let me close with a societal imperative. Here are possible outcomes to the search for life in these 3 ocean worlds. One is there's no life on any of these bodies. The second is that on one or more of these, there's life that's just exactly like us, microbial life. And the third is that it's an alien biology. And what are the implications? Well, if there's no life, and there's no evident reason why there isn't life, Europa's habitable, but there's nothing in it, Enceladus doesn't have anything, but the ocean seems to be long-lived, et cetera, that obviously has the potential implication that the formation of life is possibly a difficult thing, that it requires special conditions. Maybe it doesn't work inside ocean worlds. Maybe it requires being on the surface of a body. If we get life just like us, there are 2 options. One is that there's been an exchange of material, interplanetary panspermia, dynamically interesting, but not so interesting from the point of view of whether we're alone in the universe. Or there really is a narrow choke point for the chemical-biochemical transition, and only life like us works. Now, I would be very skeptical of that because there are many different kinds of amino acids, for example, that could work. But who knows? And that would have its own implications. The most interesting to me is the alien biology, because in the case of life in the methane seas, we would absolutely know, in the methane seas of Titan, that life had an independent origin from life on Earth. And it would say that the chemical evolution across the transition from the abiotic to the biotic, as Philip Morrison put it, from the dead to the quick, is easy, and it happens anywhere. In the case of life that has a different biochemistry in Enceladus or Europa, there we would still have to ask the question whether that life had an independent origin or whether it got transported by impacts early enough in the history of the solar system that it evolved in a different way biochemically. That's a less likely proposition than an independent origin, but we would have to worry about that, and that would probably require very detailed analysis of the genome of this cell. But what's interesting in this case is that aqueous-based life is likely to be similar enough to us that it opens up the possibility of engineering, biomedical, and ecological applications combined with the genomics that is a field that we know is flourishing today. I'm not going to go in detail into these because I'm not a biologist or a genomics expert, but there's work being done today to add base pairs to the base pairs that we have today, the 4 letters of the genetic alphabet. And although this is engineered, we know in the past that the most successful applications of novel biological techniques ultimately come from nature. The clues come from nature because nature is always more creative than we are. And so opening up the possibility of a second biology would revolutionize biological applications on the Earth. So let me close with some thoughts. There are potential societal impacts to the discovery of life elsewhere in our solar system that are not only philosophical but potentially practical as well. And they are so great that we should attach substantial importance to this endeavor. Trying to explore all of the ocean worlds on that first chart before we do the search for life on one of them is just going to be hopeless with the resources that we have. My point of view is we must decide to do some focusing on the few ocean worlds that we have the most knowledge of. At the same time, this will not mean giving up on planetology on these other bodies. Europa Clipper is a planetology mission with an enormous breadth of science. ESA is developing JUICE, which will go to the Galilean satellite system and explore them. And the decadal survey that's currently in operation, currently relevant, has as a high priority missions to the ice giants. And if we do one of those, we choose Neptune, then we can explore another ocean world, Triton, as well. But in the midst of all this, we should make sure we have the resources to explore Europa, explore Enceladus, and explore Titan. And again, even with an aggressive program, finding life is probably 20 years away. So I want to close with another quote from Carl Sagan from his final book before he died, The Demon-Haunted World. And this quote, I think, should provide some reassurance to those who are worried that the search for life will either be an unconstrained effort or will end like Viking or won't have the kind of applications, the kind of results that will further motivate planetary science. Carl was talking in general about planetary exploration, but I'll use this for the question of looking for life. Future missions to Mars or other fascinating worlds could produce results that are extraordinary and unexpected. We've seen that in planetary exploration over and over again. The thing that will prevent us from creating a fantasy, from generating a false positive or creating a mission that is poorly constrained or poorly designed, is the experience that we now have in planetary exploration, which goes well beyond what we had from Viking, and our scientific skepticism. As Sagan says, skepticism must be a component of the explorer's toolkit or we will lose our way. And so combining that skepticism that is a key tool in our trade with the 40 years of planetary exploration that have occurred since Viking will ensure that the wonders that we find are not things that we've invented in our head, but are things that are really present out there in the solar system. Thank you. Okay? Okay. All right, and I'll repeat your question so people can hear it. Right. Mm-hmm. Mm-hmm. Right. 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 Okay. So Carolyn's point is that bubble scrubbing, akin to what happens at the surface of the Earth's oceans, could enhance the organic and possibly cellular content of what's coming out into the Enceladus plume by a factor of 1,000. And thousands. And yes, I agree, that's quite possible. But I would argue that for a first conservative mission, you want to do the things that you know you can do, even without that process occurring. And if you happen to find that you've got this enormous enhancement, then you're all the richer for it. Yes. Okay, so the question is there a redox gradient on Titan? And the answer is that potentially there is in the nitrile systems, where you could have essentially different amounts of nitrogen and have some weak redox gradients. The real difficulty, though, is that most of those species have quite low solubilities in liquid methane. And so maintaining those in an environment where they can find each other and essentially react to produce the energy might in fact be the problem. Now the solubilities are higher in ethane. And of course the seas that have been investigated except for Ontario-Lacus are very much methane rich, but Ontario-Lacus is about 50-50. So in that case, you might have these things at meaningful concentrations.
So, hello, very nice talk, thank you.
Sure.
My question is, because everything takes so long, basically on a generational level, how can we make sure that the interest in space exploration and so on even prevails until the next generation, or how can we make projects to get kids even more interested in our work?
So the question was, given the long intervals between these missions, or at least their results, how can we keep the public interest? And the answer is that we use the missions that are ongoing today, and we make sure there's a healthy number of missions going, which means a mix of small, medium, and large missions, so that we're not waiting a decade for the next flagship mission. One of the points I should make is that much of what I said in terms of what could be done at Enceladus and Titan might be doable with Discovery and New Frontiers missions, and those have a fairly high frequency even though the trip times are long. So making sure that we have some overlaps between missions, I think, is the key to that. We waited a long time between Voyager at Jupiter and Galileo, and interest was still there.
Hi, my question is there a fundamental reason to expect that places with liquid water are the best place to look as opposed to places with, say, water vapor?
So I didn't quite hear your question. Is there some reason to expect that it's liquid water versus water vapor? So the only problem with water vapor is stabilizing systems within that to build structures and be able to have an inside versus an outside chemical gradients. Water vapor is something in the gas phase, things that are floating around, they will tend to float away or sink to the surface. And so it's more difficult to imagine having the kinds of structures and relationships between compounds that you would have in liquids.
Thank you very much, Jonathan. Thanks.
Sure.
Yeah, Jack. Yeah, how you doing?